Solving systems of equations by elimination. We also call this linear combinations. First example, solve this system by elimination. So notice we do not have graph paper. We have no access to technology, but we're asked to solve a system of linear equations. So we notice that these equations are in standard form. So if we just add the two equations together, the x's cancel out. We're left with y. 8y is equal to 16, and I can divide by 8, so y equals 2. That means the y coordinate of the point of intersection of these two lines is 2. Now I can take either equation. I'll pick the top one. I can substitute y equals 2 and solve for x. So I get that 5x equals 5, so x equals 1. Therefore, my solution to this system of equations is 1, 2. Notice the easiest way for me to solve this system was simply to add the two equations together because I eliminated the x terms by doing that. Let's look at another example. Here, if I add the two equations, the x terms will not eliminate and the y terms will not eliminate. But if I just multiply the bottom equation by -1 and rewrite the system, now when I add them, the y terms will eliminate. And I end up with 5x is equal to -10. X equals -2. That is the x coordinate of my point of intersection. I can use that x coordinate in either of the two given equations. I'm going to choose the second equation, which had all positive coefficients. So 2 times -2 plus 3y equals 5. -4 plus 3y equals 5. 3y equals 9, so y is -3. Now I see my solution is -2, -3. That is the point that lies on both lines. It satisfies both linear equations. And how I got that solution was when both equations were in standard form, I wanted the y terms to eliminate, so I had to multiply the bottom equation by -1 to get the y terms to cancel out. All right, example 3. Here we have two linear functions, but only one of them is in standard form. So let's take the top function. Let's rewrite it so it's in standard form. We'll subtract 8x from both sides. Now that I've done that, can you see that if I were to add these equations, neither the x nor the y would eliminate. But if I were to multiply the bottom equation by 2, now my x coefficient becomes 8x. And then minus 6y equals -4, which I can add with my top equation. Can you see that my x terms eliminate? Now let's add the y terms. I have -1y equals -6, so y equals 6. That is the y coordinate of my point of intersection. We can substitute that y value into either of the two original equations. I'll pick the second equation to substitute 6 for y. And now I can solve for x by adding 18 to both sides, and I get x equals 4. I now have the x and the y coordinate of my solution, namely 4, 6. That is the point of intersection of the two lines. Now how I solved this equation, this system of equations, was I rewrote them in standard form And I realized if I multiplied the bottom equation by 2, the x terms would cancel out. Let's look at one last example. Here we have 2 lines in standard form, but there is nothing I can multiply the top equation by to eliminate the x's or the y's. So I want to think, let me focus on my x's. 12 would be the common denominator of, or the common multiple of my x terms, right? But my y terms, I might be, well, sure, let's multiply the top equation by 3 to give me 12x, right? And I can multiply my bottom equation by -2 to give me -12x. This way, if I add them together, my x terms will cancel out, right? And I end up with -19y equals 95. And we can divide by -19, and we get y as -5. Now that is the y coordinate of the solution. Let's plug this value into either equations. I'll pick the top one. We'll put -5 in place of y. And we'll simplify this equation. Now to solve for x, I get 4x equals 0, so x is 0. So now the coordinates of the point of intersection of the 2 lines is 0, -5. That is the solution. And how I solved this one, remember, was I decided to focus on the x terms, and I multiplied the top equation by 3 to give me 12x, and the bottom equation by -2 to give me -12x.